Today's show is all about energy, from pulsars accelerating electrons to making gamma rays to a student experiment measuring the Earth's magnetic field from space using a Raspberry Pi.
We also have some pretty Hubble photos, including uncommon galaxies.
We conclude with lasers, not on sharks, but in California. All that and more right here on the Daily Space. I'm your host, Dr. Pamela Gay.
And I'm your host, Eric Mattis.
And we're here to put science in your brain.
The Raspberry Pi mini computer has allowed students and others to get experience in programming and building small electronics. Amateur astrophotographers also use them to automate their telescopes. ESA's AstroPi project recently sent one of them to the International Space Station. ESA put together a competition to get student experiments to run on the in-space hardware, and the program has its first test results out. All of the student experiments use the same hardware, called the Sense Hat. The students from a high school in Portugal programmed the AstroPi for magnetic field research. The students got data from about 3 hours of ISS orbits and were able to roughly map the Earth's magnetic field. In their paper published in the American Journal of Physics, they compared their ISS results to a professional network of satellites and ground stations that does a survey every 5 years. This survey, the International Geomagnetic Reference Network, was last done in 2020. And the students' results were close to the professionals, with a fixed variation likely caused by the local field of the station's electronics. The students tried again with 15 more orbits of data and got better results. According to the paper, the student project could be repeated on the ground. It doesn't even need to use the Pi platform, but could be done with smartphones. Faculty mentor Nuno Barros Isa said, quote, "Taking measurements around the globe and sharing data via the internet or social media would make for an interesting science project that connects students in different countries." End quote.
Mapping out our magnetic field and understanding how it interacts with solar particles is science that basically helps keep our civilization alive. After all, we're pretty sure life owes a debt of gratitude to the magnetic field, which protects us from cosmic radiation and the solar winds. And that field is generated deep inside Earth, where the outer core of our planet is made of liquid iron, spinning and swirling, creating a dynamo. Now, research published in the Proceedings of the National Academy of Sciences presents evidence of a newly discovered type of magnetic field that runs along the outer edge of the core up against the mantle. The wave oscillates over a 7-year time frame and moves westward at 1,500 kilometers per year. Lead author Nicholas Gillette explains, quote, "Geophysicists have long theorized over the existence of such waves, but they were thought to take place over much longer timescales than our research has shown. Measurements of the magnetic field from instruments based on the surface of the Earth suggested that there was some kind of wave action, but we needed the global coverage offered by measurements from space to reveal what is actually going on." End quote. The global coverage came from the European Space Agency's Swarm satellites, a trio of identical satellites launched in 2013 for just this type of observation. The data collected was combined with measurements from 2 other European missions, Germany's CHAMP and the Netherlands' Ooststad, to create a computer model of Earth's dynamo. The team suspects that there are longer period waves to be found, but obviously more observing time is necessary. Swarm is doing what it was designed to do, but I'm always delighted when a spacecraft is used for observations outside its mission, proving how creative engineers and scientists can be given the opportunity. And earlier this month, the total lunar eclipse presented one spacecraft with a unique chance to view the event from space. And that's just what NASA's Lucy's spacecraft did. Lucy launched in October 2021 and is currently heading back toward Earth for another gravity assist this October to help sling the spacecraft out to Jupiter's Trojan asteroids. This trajectory meant Lucy's LORRI camera was able to capture the eclipse from about 100 million kilometers away. Unfortunately, the time-lapse video of the event is only about 2 seconds long. It's definitely a blink and you'll miss it clip. We'll have to link to it on our show notes at dailyspace.org. So go take a moment to enjoy watching the moon just sort of blip into darkness. That's enough with the latest in spacecraft missions. Let's go look at bigger objects like stars, planetary nebulae, and galaxies. Stay tuned. I would like to start this story by pointing out that solar scientists can be super dramatic in their naming. Astronomers, we're just bad at it. But for solar scientists, everything is a crisis. I grew up hearing about the solar neutrino crisis, and with that solved, now I'm learning there's a solar abundance crisis. Back in 2009, the sun's chemical ingredients list was measured to a level of precision that should have made models of the sun match what we see beautifully. But they didn't. The sun is a mass of incandescent gas that shakes like liquid on a speaker playing a long, low tone. We can see these waves reshaping the sun's surface, and the size of the waves is directly related to the volume of the part of the sun that is resonating and the density of the material inside. This is like how the notes you can play when blowing in a soda bottle are related to the size of the empty part of the bottle, and whether you knew it or not, if the bottle is filled with normal, mostly nitrogen gas, you get a different tone than if it's filled with something else. It turns out that those 2009 solar measurements predicted a sun that should resonate with a different set of pitches than the ones our sun's surface is observed to actually play. And the solar scientists named this mismatch the solar abundance crisis, because it seemed to imply that our understanding of what is in the sun's atmosphere might not be right, and to them this was a crisis. Again, they are dramatic in how they name things. Turns out the problem wasn't in the measurements of the sun's ingredients. The problem was in our interpretation of those measurements. In modeling how stellar atmospheres are heated and how they excite different atoms to absorb or emit light, it has generally been assumed the sun is able to effectively spread heat through its atmosphere and is in what's called local thermal equilibrium. This implies that even though the sun's atmosphere is heated by roiling bubbles of rising and falling gas that are all different temperatures, like the convecting blobs in a lava lamp, somehow the atmosphere can be modeled like everything, at least at the local level, is a nice smooth distribution of temperatures. But in a new paper in Astronomy and Astrophysics with first author Ekaterina Maj, researchers in a team led by Maria Bergman try modeling the sun using calculations that didn't assume local thermal equilibrium. This small change makes the maths a whole lot harder, but also makes for a more realistic description of how energy moves in lower density areas like the sun's photosphere. And it turns out that those changes in the models changed what ratios of ingredients the sun needs to have to produce the interrupted rainbow of light we see. According to Maj, quote, the value for the oxygen abundance was almost 15% higher than in previous studies, end quote. This change made the sun better match both the compositions of primitive meteors that are representative of the early solar system and brought the results from the spectra and those, well, we call it helioseismology, that shaking of the surface of the sun, brought it all into alignment. As they state in their press release, crisis resolved. Bergman goes on to explain, quote, "The new solar models based on our new chemical composition are more realistic than ever before. They produce a model of the sun that is consistent with all the information we have about the sun's present-day structure, sound waves, neutrinos, luminosity, and the sun's radius, without the need for non-standard exotic physics in the solar interior." End quote. At the end of the day, it seems it is a good idea to check your assumptions when maths and observations don't match. Sometimes our simplifications create false emergencies, and all it takes is a bit more complex calculations to see things as they really are. Our sun is a main sequence star. This means that sometime in the far distant future, about 5 billion years down the road, our star will puff up into a red giant. Even further down the road, it may blow off enough material to become a white dwarf. In the process, expanding shells of gas and dust might be ejected and form a planetary nebula, which would be gorgeous to see, if any of us were still around in our robot bodies to do so. In the meantime, we have other planetary nebulae we can observe that can help us understand the chemical evolution of stars and even galaxies. A new paper on archive.org examines one such planetary nebula, IC 4997, using the 500-meter aperture spherical radio telescope, or FAST in China. This particular planetary nebula is about 8,000 light-years away in the constellation of Sagitta, and has a relatively high surface brightness and bright central star. Additionally, IC 4997 is rapidly evolving, which makes it a great observational target. Analyzing the radio data, scientists detected neutral atomic hydrogen absorption in IC 4997, which is a fancy way of saying there is cold hydrogen gas. And the atomic shell of the planetary nebula consists of about 17 septendecimal hydrogen atoms. That's 17 followed by 54 zeros, a number I never thought I would write, let alone say. The evidence further suggests that this particular shell was ejected at least 1,000 years ago, but, and this is pretty common when it comes to planetary nebula, the nebular mass is still less than expected. All of that is a long-winded way to say that the data collected is interesting, but doesn't solve the ongoing missing mass problem that seems to be common with planetary nebulae. However, FAST seems to be more up to the challenge, and the team plans to look at more planetary nebulae in the future.
Before we get into the heavy science in our final segment, here's a pretty picture. The larger of the two galaxies in this picture, collectively called IC 4271, is the Seyfert galaxy. Named after Carl Seyfert, these are galaxies with a black hole in the center, making them glow brighter than other galaxies without black holes. Specifically, the larger part of IC 4271 is a Type II Seyfert, because it glows in mostly infrared and optical light. This image is from a survey where astronomers looked for pairs of galaxies, but only those where one is in front of the other as viewed from Earth. Hubble's Wide Field Camera 3 is capable of seeing ultraviolet through infrared. In this image, ultraviolet light is colorized violet, while near-infrared is shown in red. Coming up, scientists continue to try and understand just how certain high-energy events work. Stay tuned.
There are some research papers I read and realize I'm really glad I'm not in grad school anymore, because the paper I'm reading would be a homework problem. There are a remarkable number of problems in astronomy where lots and lots of folks have said, well, that could be X, but no one really wanted to do the maths to figure it out. Then, once someone has done it, lots of folks assign that problem as homework, using the published paper as a solution guide. A remarkable amount of grad school was learning how to find the papers our homework problems were stolen from. I am still bitter about the homework problem that came from a paper that resulted in the original researcher getting a Nobel Prize. That's not fair. Anyways, a pair of new papers in the Astrophysical Journal Letters and Nature Astronomy, led respectively by E. Diona Vilhama and R. Lopez Cota, looks at the regions around young neutron stars and asks the simple question: are the magnetic fields sufficient to accelerate electrons to the kinds of speeds necessary for them to produce gamma-ray light when they collide with photons? They did this exercise specifically to prove that this is not what was happening. But the math replied with, well, actually. And they found themselves proving that yes, the magnetic fields around young stars are that strong. Here's what is happening. As the young neutron stars, less than 200,000 years old, spin, they generate powerful magnetic fields. Their surroundings aren't exactly empty. Neutron stars are the leftovers of massive stars that had previously undergone all sorts of mass loss. And the young objects are extremely hot and produce ionizing radiation that can separate electrons from their atoms. Those electrons in the powerful magnetic field get accelerated just like the electrons in the Large Hadron Collider, just more so. While some of these electrons will eventually reach Earth as cosmic rays, their paths are hard to trace because they are affected by intervening magnetic fields from other stars and black holes. Some of these electrons, however, interact with photons in the vicinity of the pulsar and pump the energy of the photons to the gamma-ray part of the spectrum. These extremely high-energy bits of light then fly to Earth on straight lines that ignore magnetic fields. We knew that pulsars had gamma rays, but the why of it wasn't detailed out prior to these papers. Now, we have nice, consistent answers to both where do some cosmic rays come from and why do pulsars produce gamma rays? It is a beautiful result, and I'm really glad I don't have to replicate their math. Sometimes the work being done in labs is astounding, to say the least. And when you find out that the experiments involve high-power lasers, well, how can you resist reading more? Scientists from Princeton University, the U.S. Department of Energy, Princeton Plasma Physics Laboratory, and the SLAC National Accelerator Laboratory have found a way to simulate the high energy of a magnetar in the lab. They're doing this to get at understanding what fast radio bursts are and how they happen. Their research was published in 2 journals, Physics of Plasmas and Physical Review, and was led by Keenan Q from Princeton. Magnetars are neutron stars contained within incredibly strong magnetic fields that basically convert the vacuum of space into a strange matter-antimatter plasma, or pair plasma. They're neutron stars like the prior story, just more so. This particular soup is different from the plasma of the sun because it only has electrons and higher mass ions, and of course that leads to strange behavior. Creating this particular type of plasma in the lab requires not using magnetar-strength magnetic fields, but rather lasers. As Q explains, quote, "Rather than simulating a strong magnetic field, we use a strong laser. It converts energy into pair plasma, which then shifts the laser pulse to a higher frequency. The exciting result demonstrates the prospects for creating and observing pair plasma in laboratories and enabling experiments to verify theories about fast radio bursts." End quote. Before anyone gets too excited, Q notes, quote, "No lasers are strong enough to achieve this today, and building them could cost billions of dollars. Our approach strongly supports using an electron beam accelerator and a moderately strong laser to achieve QED pair plasma. The implication of our study is that supporting this approach could save a lot of money." End quote. The simulation is expected to be tested at SLAC in the near future, and we look forward to hearing more about this fascinating work. This has been The Daily Space.
You can find more information on all our stories, including images, at dailyspace.org. As always, we're here thanks to donations of people like you. If you like our content, please consider joining our Patreon at patreon.com/CosmoQuestX.